may remember, if you watched our presentation on numeracy, that we can perform what we call operations on natural numbers, and the natural numbers are those numbers which start with 0 and then are formed by adding 1 to the previous one in the sequence. So we have a natural sequence of natural numbers starting with 0, then moving on to 0 plus 1, and then 1 plus 1, which is 2, and then 2 plus 1, which is 3, and so on and so forth. And for any pair of natural numbers, we can operate on them, and common operations with which you'll be familiar are the operation of multiplication, and the multiplication sign is that, division, and that's one way of writing a division sign. I'll just emphasize that dot at the top. Addition, and that's the familiar plus sign, and subtraction. So what we do is we operate on two numbers. We have one in the box here, and then we have one of these four symbols. There are actually other operations that we can perform on natural numbers, but let's suppose we have a division sign and then another natural number here. Now, when we write something like that, as I said in those presentations, that is a number. It means this number, whatever that number is, let's call it y, is divided into this number, and let's call it x, whatever x happens to be. And then we can find out, we can write that number more simply, and we'll say that that number is z, for example. So x divided by y equals some number z. Now we can perform operations also on sets. Let's suppose that, we'll do it in capital letters here, x and y are sets. And let's represent them graphically. Let's suppose they are sets of balls in bags, and let's suppose that we have, or boxes or trays, and let's suppose we have one which is set y. Set y is all of the balls in this box, and then let's suppose that we have another, I'll just choose another color here, set x, and x are all the balls in this box. Now this box is sort of an odd shape, and part of it sits within box y. So this is box x. Now let's suppose we've got a number of balls. We've got a red ball in box x. We've got a yellow ball which is also in box x. We've got a light blue ball which is not in box x but which is in box y. We've got a grey ball which is in box x but not in box y, and we've got a dark blue ball which is in both of them. And then what else shall we have? Let's have a sort of a pinky ball which is in y but not x. Now let's define these sets. We have x is equal to the set which contains the red ball, the grey ball, looks more like a black ball again, doesn't it? And I'll separate these with commas, the yellowish ball, and the blue ball. So those are all the balls that are in x. Sorry, that's supposed to be a comma separating those two. Right, so we have these four things, 1, 2, 3, 4, and they are in x. So that's what set x happens to be. And what about set y? Let's write that in green. Y is the set, I'll actually write this in blue, it's easier to see. So y is the set. How many balls? We've got 4 balls in y as well. We've got a light blue ball. That's that one over here. We've got a sort of purplish ball. And then we've got a yellowish ball. And then we've got the blue ball. again I'm going to separate those with commas. Those are supposed to be commas. Right, now we can operate on those two sets in just the way that we operate on numbers to form new sets. And how might we do that? Well, let's first of all define an operation which we call union. This is something we do to sets, but we don't do to natural numbers. And we write it with a big kind of a U sign, like that. And the union of sets x and y, so we write x union y, is itself a set, and it is specifically the set of all of those things which are either in x or in y or both. So x union y is the set of things in x or y or both. Okay, now let's just define x union y by reference to all of these boxes of balls. X union y, what is it? Well, it's a set, first of all. And let's just write it in these curly brackets again. And what is it? Well, it's the set of all of the balls, either in X, so all the balls in X are the red ball. I'm not going to bother to separate them with commas this time. The grey ball, the yellowish ball, and the dark blue ball. Or in Y, and well, we've got this yellowish ball and the dark blue ball are in Y, and then we've got some other balls in Y. We've got the light blue ball and we've got this purplish ball, or both. Well, the yellow ball and the blue ball, those two are in both. So X union Y is the set of 1, 2, 3, 4, 5, 6 balls, all of these 6 balls that are in either X or Y or both. Okay, now in addition to union with this U sign, we can operate in sets in two other ways that we're going to discuss. And our second operation I'm going to call what we call intersection. Intersection. And again, you'll have to forgive my writing. And intersection is just this sign. The symbol for intersection is just this sign turned upside down. So now we write the intersection of two sets is again another set, and the intersection of the two sets x and y is x, and that funny upside down u, x intersect y. And what does that mean? Well, it means this. X intersection y, the intersection of x and y, is the set of things which, my writing is terrible, are in both, not either, but both x and y. Now, what is the intersection? Again, going back to this diagram, what is the intersection of x and y here? Well, x intersect y, again, is a set. When the intersection of two sets is a set. And it's the set of things which are in both x and y. Well, which of these things are in both x and y? The red and the grey balls are in x but not in y. The light blue and the purplish balls are in y but not in x. but these two balls, the yellowish ball and the bluish ball, that's the yellowish ball and the blue ball, are in both. So the intersection of x and y is, in this case, the set containing the yellow ball and the blue ball. Okay, so I've just undone that. So now we've defined two operations on sets, union and intersection, and now I'm going to define a third operation on sets, and that is the operation of subtraction. Now we have an operation of subtraction which we perform on natural numbers, don't we? But this is slightly, well, the idea is somewhat related, and the sign for subtraction is the same as in arithmetic when we operate on numbers, and it's just a horizontal line like that. And let's take a look at what it means. Well, the subtraction of y from x is again a set, and it is the set of things which are in x but not in y, and not in y. So again, let's just illustrate the operation of subtraction by reference to this diagram. And what have we got here? X minus y is equal to, well, it's a set, so we put it in these curly brackets. That doesn't look too much like a curly bracket, does it? But there we go. X minus y, the set of things which are in x and not in y. Well, we've got four things in x: the red, the grey, the yellow and the blue, but the yellow and the blue are in y, so we take them away. So what are we left with? The red and the grey ball. So let's just close out these brackets. I don't need very much space between the brackets because we've only got two things in x subtract y, and that is the red ball and the grey ball. So now we have these three operations, these operations on sets: the operation of union, the operation of intersection, and the operation of subtraction.